All right, welcome. In this video, I want to talk to you about a reinforcement learning technique called Q-learning. So this technique was first presented in 1989 and gained popularity in the 90s by this gentleman, Christopher Watkins, who came up with Q-learning as part of his PhD research. Again, that was in 1989, and I've shared with you here an article called Q-learning, written by Christopher Watkins and Peter Dayan, who in this particular article that came out in 1992, they prove the convergence of Q-learning under certain stipulations about the learning rate. So what is Q-learning? Well, Q-learning is going to be an alternative to the value iteration algorithm that we've been looking at in our last couple of videos. It's a sort of an expansion on the value iteration, so it applies a lot of the same techniques or ideas that we had in that algorithm. But it is called model free because it doesn't try and learn a model like the value iteration algorithm or algorithms that use value iteration do. And it also has exploration as kind of a key component of the algorithm, which is important because in the value iteration algorithm, we kind of separated those two parts out. You go explore to learn the model, and then once you learn the model, you apply value iteration, and they're kind of separate. In Q-learning, they're kind of kept together. Now, what it means to be model free is that Q-learning does not need to know the model. And again, what is the model? The model is the transition function. So you don't need to know what state you're going to arrive in given a particular action from a different state. It doesn't need to know the reward function. It doesn't need to know how much reward you get from entering a state or taking a particular action. And it doesn't need to even learn that model in its process. So during as it's learning, it doesn't try and learn a model as it goes. So nowhere in it does it keep a model. There's sort of an implicit model in there, but it doesn't try and learn a model. What that means is it works just as well in a deterministic environment as it does a stochastic one. So the differences between those models does not matter to Q-learning. And so much so that it can even be applied in dynamic environments. And again, dynamic meaning changing over time. Okay, so we can and you know, as long as it's not changing too rapidly, the Q-learning is going to learn new pathways in a changing environment, which is again very beneficial. So how is it that Q-learning is able to operate without having a model of the environment, without understanding the transition functions and the reward function? Well, the way it does this is instead of trying to learn the value of states, the utility of a state, of being in a particular state, what it learns is the value of the action that got you to that state, or more specifically, the state action pair. So usually you were in an old state, you took an action, and then you arrived at a new state. Well, we don't apply the value to that new state, we apply the value to the pair, the state action pair that got you there. So different state action pairs could have different Q values arriving at the exact same state. Okay, so this is one thing that's going to be different. So I've got this depicted sort of in my little example over here, that instead of having one value in a state that represents that state's value or utility, we're going to have that, in this case, 4 values in that state, one for each action that is possible in that state. And so here I just made up some numbers. These aren't part of some experiment I was doing, but we might imagine that our robot has assigned the action that moves us to the right here, the score of minus 99 or minus 100. I only put 99 so it had 2 digits and didn't look ugly here. But since the actual value of this pit might be minus 100, it may have learned like moving in that direction is minus 100. Now the other states are going to take into account, or the other Q values here are going to take into account the discounted utility of distant action. So this 75 here might be a 75 because to get to the pot of gold, which is our 100, it has to move through this other state. So it's saying the utility of going this way is 75 because it's in the direction of the pot of gold. And for that same reason, the utility of running into this wall would be less. But it's not as less as moving backwards. Moving away from the gold is probably worse than just bumping into this wall and staying where you are for a time. So again, I just kind of made up some utilities here that might, or they're not utilities, we call them Q values. Q stands for quality, or that's where Christopher Watkins got the Q from. And so we might be storing these Q values, which really are just estimations of this state action pair. Okay, so now when we want to update a Q value, so maybe we have taken an action from a state and we now want to update the Q value that us estimated the value of that state action pair, we're going to once again apply the Bellman equation like we've done in the last couple of videos. So the Bellman equation, again, is just a way to update the value or the estimate of utility or value of this particular entity. The only thing we've changed is the entity. It's no longer the value of a state, it's now the value of a state action pair. So the equation itself probably looks fairly similar. We have the new value is going to be updated in terms of the old value, adding on some additive part. This is the new information. Let's look at these different pieces. I've simplified it a little bit from my previous video just to make this equation have less notation in it. But this R, this is the reward that we received from this state action pair. So when we carried out this instance, this is the reward we received. Now this is an instantaneous reward, meaning it's not some average reward that we've calculated over time. This is the actual reward that we received right now. Okay, so even if this reward is different than the last time we arrived at this state or the last time we took this state action pair, that's fine. In this update, we just take the present current reward. The other thing we do is you'll see this state S prime. This is the resultant state that we got from taking this action. Again, action A from state S. So in this state action pair, we arrived at state S prime. Well, that doesn't have to be the same state that we arrived at last time we took this state action pair. This could be a probabilistic function. So all we're doing is whatever specific state we arrived at, we're going to apply our Bellman equation to that state. Now remember, what we do in that next state is we maximize over all the actions in that state and we try and figure out which would be the best action, because this is us looking into the future saying, well, if in that next state I just followed the best actions every time, what would be the utility I would gain from following the best action? So that's why we look there and we maximize over all the actions we can take. Again, we see our discount factor showing up. This is the same discount factor we've been using in the last 3 or 4 videos about value iteration. We've just got a discount factor here. So what's new about this equation, other than that we've swapped out the value of S for the Q of SA, is that we've also added in this learning rate. So something that's kind of come along with Q learning and has become more popular as we've applied it in the 90s and more recently, is we've started applying this learning rate alpha, which tells us how much we bias old information and how much we bias new information. So remember, this component here, this QSA, that's the old value, that's the old Q value. That's incorporating all of the information that's come up to this point. This term over here, this term is all the new information. That's everything we've learned right now, the new state that we've arrived at, the new reward that we've got, okay? So all that information is new. So we can change alpha between 0 and 1 to determine how much we want to weight these two components, okay? So for instance, if we had an alpha of 1, that's saying new information is the only important information. Old information should always be discarded. If we set our alpha to be 0, it says new information is irrelevant. No more learning should be done. We've learned enough. Shut off learning. Okay. Both of those extremes are very rare. Okay. More likely, we're going to have a small constant alpha rate. There are other strategies that change alpha over time, which I think might be beneficial in certain environments, but it's very common to have maybe a small low learning rate of like 0.1, so that you're always engaged in some learning, but new information isn't dwarfing old stuff. That's helpful in a stochastic environment where new information might be kind of random. Remember us in that last video pulling the lever and getting a 97 or a 94 when we're randomly picking a number between 1 and 100. That's very instantaneous information that might not be as helpful. So one important aspect of Q-learning updates that's going to be important is that we can only do an update when we actually observe that state action pair. And the only time we observe a state action pair is when we actually do the action. So the only time we can update a Q value is if we've executed that state action pair. That means exploration is very important to Q learning. It means we need to go out in the environment and try different actions so that we can observe them and update their Q values, hopefully so that the law of big numbers can kick in and we can get those Q values converging on their actual values. Okay, what that means is exploration is central and critical to Q learning, and we need to have an exploration strategy to do exploration in Q learning. So there's not a built-in way to decide when to explore and when to exploit. We still face that trade-off, but it's built into Q learning that exploration is going to be an important component. So you are going to want to, you're not going to have any offline algorithms that are just pre-computing everything. Instead, you need to go out there and explore the environment. So epsilon greedy, which we looked at in an earlier video about exploring deterministic environments, is just as useful in a stochastic environment. So we can use epsilon greedy exploration strategies. Remember, that's giving us some percentage epsilon that we're going to use to decide to explore, and then the rest of the time we will exploit. It is very common to change that epsilon value over time. Started out high to encourage exploration at the beginning and reduce it over time to encourage exploitation as you learn more information. A real cool and interesting way that you can encourage exploration in Q learning is to set your initial Q values to be really high. Okay, now why might that be? So imagine there's an unexplored part of our region and we've set its Q value to, I'm going to pick a ridiculous number, 1,000. Okay, so in this environment, 1,000 is much bigger than actually getting to the pot of gold. So what that's saying is it's being very, we sometimes call this optimistic, an optimistic Q learning, because it's assuming that any part of the environment that you haven't explored is full of goodness. So that when you get to a part of the world that you haven't explored and you're comparing it and you're deciding, should I explore or exploit, the exploitation paths are all look bad. The exploration paths all look good. So only once you've evaporated all those exploration paths and all of them have been explored and replaced with actual values, then then you might be able to kick into that exploitation phase and start following the paths that you're interested in. So this is just a very common way. You can think of it as maybe tricking the Q learning into exploring, okay, or encouraging it to explore when it might otherwise not do that. All right, welcome back to our simple environment here. I've now got it set up to do Q learning. And so in Q learning, I've got the Q values associated with each of the actions. So moving up from this square has a Q value. I've initialized them just to the utility of the current state, I believe. And so that means that these Q values are not optimistic, like I just mentioned. These are kind of pessimistic Q values that are going to make exploration in exploitation context less likely. So let's turn our agent on. Notice there's no way that I can just tell it to compute all the Q values like we were doing in the value iteration. I could just click value iteration, value function here, and it would compute all the values. Well, we have to explore. So I'm going to start out my agent here. Okay, that agent's jumping in the pit a few times. But you can see as it's going, it's computing Q values. Its exploration is very high. That's why it keeps jumping in the pit. But it's estimated the Q value of jumping in the pit there, well, it was for a while at 105 or 106. We noticed it fluctuate and go to 49. What's up with that? Well, that's because it maybe moved to that state and slipped into this state instead. And so it updated its value and said, okay, that actually looks like it might be a good action to take. Only by taking that Q value a lot and updating it a lot are we going to be able to get it to settle into a point where it says, no, most of the time I go that way, I keep falling into that pit. So it's better for me to find some path that's more advantageous for us. Now, I'm curious to see, it's still learning, but I'm curious to see what its values are going to be for the two paths. So right now, it looks like it thinks going up is better than going to the left. Ooh, see now it's, okay, we saw that number change. It's going really fast here. But every time it tries to go up there and slips into the pit, it goes and updates this Q value to a negative, which affects it. So now we see, okay, it's changed its mind. But for a while there, it decided, no, the safer way to go is run around the outside. Okay, now it keeps changing its mind. It's still exploring quite a lot. But let's maybe Let's speed it up. No, actually, let's do this. Let's change this to 10. And I'm going to try a new agent now. So it's going to explore a lot at the beginning, but it's going to very rapidly turn down its exploration and try and just exploit. So right now, it hasn't really found a good path yet. But now it's found the short path. So if it's exploiting, it's going to try and exploit the short path. It now doesn't quite like that short path, but the long path it really hasn't found yet. Oh, did you see that? It was running into the wall. It's running into the wall. Why is it running into the wall? Oh, it's found a real fun path. So what it's doing is it says, yeah, I can take the short path, but instead of going up, which tends to kick me into the pit, I'll just run into this wall and hope it slips me up to the top. And so, okay, now it's updated, so maybe I should go up. But for a while there, it had found an interesting way to get around slipping into the pit, which is try and move into that wall. See there, it's doing it again. Move into that wall a bunch. And it's interesting because when it moves into the wall, it keeps lowering the utility or the Q value to a point where it says, well, maybe I should explore that up path again. And then when it does, it changes it. Actually, I really like it. I think it's settling in now because its exploration is very unlikely that it's probably going to stick with this path. And I think this is a real cool example of how an agent might find a path that you might not expect. So it's happy to move up here because it doesn't mind slipping back and forth here. And it's happy well, the only chance that it falls into the pit now is that first step. When it makes that first step to the right, it might slip into the pit. Otherwise, it's found a path to exploit, and it's a short path. So I'm really excited about that. I like that. Let's move to the ice bridge now. So the ice bridge was I created this particular problem or this particular environment to try and test my Q learning. It's taking that pit problem that we were just looking at to an extreme. So instead of having one pit that you might fall in as you walk past it, we've got 6 pits that you might fall in that as you walk past it. So let's leave it on these settings for the moment. Actually, let me turn on my fog of war and let me make it a little bit better explorer. So I've turned on exploring, which means if it sees an empty space around it that it hasn't explored yet, it will try and go in that direction. And I've also turned on drunken sailor, which means it's not going to backtrack. So I'm going to try it again. That's just going to hopefully encourage it early on to find a pot of gold as soon as possible. However, because it's got Explorer on, it's going to walk past a lot of these pits and they're going to be unexplored, and it's going to try and jump in them like that. So if we get lucky, it will make its way to the bottom. Okay, we'll try that again on a little bit quicker and with less decay. So I've changed my decay back down to 100. Or every 100 ticks it decays so that it will be doing more exploration. But you'll see I've just got a couple unlucky. Well, okay, there we finally found a pot of gold. Unlike value iteration where that can trickle back a lot, we won't be able to get any trickle back of that until we go visit that part of the map again. So now we found 2 pots of gold. It's still struggling, but notice as it's moving, it's spending more time in the middle. Okay, it's made some interesting updates. It's going back and forth a lot because it's getting confused by its Q value up there. It's not sure, so it moved back and forth until they stabilize, and then it realized, oh, to get that good value, I need to go down. Now, let's maybe turn on our solution here. Look at what we're seeing. Specifically, I want us to look at what this is doing is pointing out the optimal policy according to the agent right now. So based on its Q values, which cell should it move in to get where it wants to go? What we'll see is for a lot of these cells that are along the edge, it says move away from the edge. And that was different than the value iteration algorithm. The value iteration algorithm says, it's okay. We're okay with that risk. This one luckily is going to push us into the middle. Okay, and what that means is, say we're moving down and we slip into one of these squares, it's immediately going to tell us step back away into the middle. So the risk of falling into those pits becomes very low. Okay, the other thing you're going to notice is there's some idiosyncrasies about the route that it's taking. For some reason, it likes to go back and forth here a lot before it moves down. And that's just because the way it has explored the environment, it hasn't effectively explored all of its options. So some of these Q values are imbalanced. So for instance, here in this cell, it happens to, when it gets to the cell, it moves left. And when it moves left, it reinforces that moving left is good. And it never has a chance to re-explore going down and reinforce that that might actually be better. Okay, so nonetheless, it's found a path that's pretty successful. Okay, at least now it's winning every time. It's not falling into any pits. Okay, so again, this is sort of an interesting application of Q-learning. I want to do one last example. So now I'm going to do a maze. Okay, I'm going to turn my solution off. I'm going to delete some walls. I usually like to delete about a dozen walls, and I'm going to add some pits, a couple pits in there. Do a new maze. Make sure there's an actual path to the outcome. Okay, there is. I don't really like that one. Let's try another one. Okay, does this have a path? Yes, but it's a long one. There's a couple long paths, and there's a pit right in the way. There's a couple of dangerous pits. So let's try this one out. Okay, so quite early on was able to find the path. Again, I've got it on really fast here. We've got set up here exactly the same scenario that we had with the 4x3, which is this pit is right. You have to cross past this pit to get into the gold, and it's now confused over here. It doesn't know which way to go. Maybe it will learn to walk into this wall. It looked like it jumped. Yeah, okay, it walked into the wall. So it's learned how to walk into that wall now. So when it gets there, hopefully, yeah, it runs into the wall until it slips into the gold. Very cool. I'm really excited when it finds solutions like this. So again, this is one of the benefits of using AI. Instead of just trying to train or build something explicitly, this will find maybe examples that you haven't been able to find before. All right, so this particular agent is struggling with this harder maze, although it has found a way, and it seems to be avoiding falling into the pits. I'm going to let it go for a little bit on my own, but I do want to thank you for watching this video on Q-learning, and I'll see you again in that next video.